There are several different ways that we define acids and bases, and there were quite a few different scientists that were involved in defining what they are. You are responsible for knowing both definitions. The first one we talk about is Arrhenius. Arrhenius defined an acid as a substance that increases the hydrogen ion, or what we call a hydronium ion concentration. And I never even learned anything about hydronium ion. We didn't really talk about it until I got to college. But it's good that you write that down. A hydronium ion is H3O, and it's a +1. So it says, an acid is a substance that increases the hydrogen ion or hydronium ion concentration in an aqueous solution. So in that first example, we see hydrochloric acid or hydrochloric acid in water. It forms an aqueous solution. The hydrogen dissociates from the HCl, from the Cl, and it gets picked up by a water molecule. That forms the hydronium ion. We can look at it in more simpler terms. If we just put the HCl and showed its dissociation, that's the second equation there. We have the hydrogen ion and the chlorine ion right there. It's the arrow showing the movement of the reaction. It didn't translate on here. So it's just the yield sign. An Arrhenius base is a substance that increases the hydroxide ion concentration in an aqueous solution.
Was that 2 R's? A-R-R-R.
A-R-R-R. I'm sorry, where? Aqueous?
No. Arrhenius. It's A-R-R.
Oh, Arrhenius, I'm sorry. A-R-R, yes. A-R-R-H-E-N-I-U-S. I can go back. I'm going to make sure all of these PowerPoints are in Google Classroom so you can access them as you need.
Those, like, equation things, or no?
They're good examples. You will see practice on those, especially these. Yeah, those two.
Just practice.
Are we good? Okay. Guys, you don't have to write every single thing. You need a quick notes. Arrhenius acid, Arrhenius base. What's the symbol we use for concentration? Yeah, that is the SI unit, molarity. But what is the symbol we use to identify concentration? We did it. We saw it in our equilibrium. The brackets. The brackets identify concentration. All right, are we good? Okay. Do I need to go back? The second definition that you need to know is Bronsted-Lowry. And if my memory serves me correct, the two actually didn't work together, but they were kind of working around the same time and kind of ended up at the same conclusion. Their definition, in my opinion, kind of encompasses more bases to be identified, where if you look at Arrhenius's definition of a base, basically says that it has to have a hydroxide ion in it in order for it to be a base. And there are some substances that are bases that don't necessarily or definitely act like bases and do not have that hydroxide ion in them. Bronsted-Lowry then identifies an acid simply as a proton donor. And we can go in a reaction. And we can go into detail about that briefly. In fact, I want to, just to make, because I've brought it up with you guys before, but it's been a hot minute. So let's think about this for a second. We know that, or what we've seen so far from Arrhenius' definition, an acid increases the hydrogen ion concentration. But let's think about real quick the structure of the hydrogen atom anyways, as it is. In its neutral state, let me see if I can write on this. In its neutral state, how many, let me see. I don't know if this is going to work. Hydrogen. How many protons does hydrogen have? It has one, right? One proton. How many electrons? If it's neutral, how many electrons does it have? One. How many neutrons does it have? It depends on what?
If it's ionic or not.
Okay, no.
Is that not because the mass
Jordan, why does it have none?
because the mass minus the protons gives you the neutrons, and the mass is 1 estimated, so 1 minus 1, 0.
That's right. If we take the atomic mass minus the atomic number, that tells us how many neutrons there are. So remember, the mass that is on there, that is the average of all the isotopes that exist for hydrogen. And it's closer to 1 than another number. So 1 minus 1 is 0. So generally speaking, the most common isotope of hydrogen that exists doesn't even have a neutron in it. So if hydrogen loses its electron, what does it have? No, we just said it doesn't have any. If it loses its electron, what's left?
Proton.
It's just the proton by itself. So when you're going to start hearing more, a proton donor, that's referring basically just to this hydrogen ion that's lost its electron, but it's a hydrogen. Does that make sense? Is that confusing?
It's kind of confusing.
It's not confusing. It's a hydrogen atom that lost an electron. Now, and Bronsted-Lowry defines the acid as a proton donor. It's because something has given up its hydrogen, basically. And when it did that hydrogen lost its electron that was keeping it there. So it's just this proton that's just kind of hanging out, basically. Not hanging out, because when we say that, like, it's not like you just can just find one hydrogen all by itself. Hydrogens don't exist like that. But to think about it theoretically, we can think of it as this moment, this one little millisecond of a millisecond, where it's like by itself.
So like basically,
The fraction of a fraction of a fraction of a second, where it's like,
it's like
just a proton. It's even faster than that. It's
Okay,
like,
let me
no, that's too slow. Way too slow. It reminded me of like Karate Kid when he's like trying to go after anyways. You guys probably haven't even seen that movie. All right. Anyways, I just wanted to explain why you see proton donor, but what you're going to see is the hydrogen being donated. And we refer to that hydrogen ion as a proton because all it is a proton. Bronsted-Lowry defines a base as a proton acceptor in a reaction. And so wherever that proton goes becomes the base. And we'll look at different reactions and identify basically